Hello, I'm Daito Manabe. Thank you all for this precious opportunity. I was looking forward to attending the event, but I am really sorry that I cannot make it to come to Paris and be on the stage to meet you all because of this severe coronavirus situation. I really wanted to go, but I am also responsible for my company and family and cannot ignore the small risks of the virus by going overseas on my own decisions. Again, I appreciate you for letting me join remotely like this. It is disappointing that I cannot join the discussion session, but I am grateful if my talk gives you some inspiration. Okay, so I have been creating works themed on artificial synesthesia while working on other projects relating to dance performance or physical and body experiments. So this is my old work called Squalite, which is collaboration work with the amazing researcher Alvaro Casinelli. So Squalite is prototype musical instruments capable of generating sound in real time from the lines of doodles as well as from the contours of three-dimensional objects nearby. Yeah, so Squalite implements gestures, shape, and color to sound artificial synesthesia. For a limited time, I will skip the detailed introduction, but a lot of research about the relationship between shapes and sound, or creative works that translate shapes into sound, can be found in the long history. I created this work along with those past examples and experiments, and I have been trying to find different approaches than synesthesia. So that's when I got to meet to Dr. Kamitani. My introduction to Dr. Kamitani was when I found brain decoding technology on researching machine learning and the brain in 2012. It was around 2014 that I got to meet him when I visited his lab and had interviewed him. The interview ended up being 3 hours long, where he explained me brain decoding technology in detail, which I really appreciate. Since then, I had been dreaming of a collaboration with using decoding technology. And finally, 3 years later from that, I offered collaboration and we started working together around March in 2018. We've done some installations and we created a live version of this project for last year's Sonar Music Festival. Okay, so let me explain his research instead of Dr. Kamitani. So this is the sheep's brain and the brain consists of neurons. I'm showing the neural fibers imaged by electron microscopy. In the brain and in neurons, electrical signals propagate through this electrical fiber. You can pick the electrical signals by sticking the electrodes inside the brain. What you hear is the sound of neuron. So, electric signals are turned into sound and electrode is inserted in the animal's brain and this image is what the animals are seeing. So this video is a historical study by Hubel and VCA who won the Nobel Prize for the discovery of orientation selective neurons. Orientation means the angle of this line. So, and later in 30s, people found more complex features are extracted at other areas in the brain. In modern neuroscience, we regard the brain signals as codes or coding, which represent perception or our mental state. So we think as if the brain signals are binary signals in a computer representing audio, visual, or text. I'm showing Dr. Kamitani's early attempt at decoding fingers movement. Here, the subject, human participant, is in a brain scanner called MRI. The subject is doing the rock, paper, scissors movement. The task is to decode from the finger movement to the brain activity pattern so that the robot can mimic the hand movement. The task here is to tell whether this person is doing or thinking rock, paper, scissors just by looking at his brain image. It is difficult to distinguish these patterns, but there are some commonalities within each group. That's why we are able to decode. Then Dr. Kamitani thought of letting the machine do pattern recognition of brain signals, which cannot be distinguished by our naked eye. So in 2005, Dr. Kamitani presented the first machine learning based decoding study. So we look at the oriented grading again. In the middle, we have a decoder, which is machine learning part. This is a mathematical model whose parameters are adjusted using trained data. So we need some data from experiments to adjust parameters in this decoder. Once it is trained, we can analyze new data to make predictions, which turns out to be very accurate in predicting which angles the grating is presenting. This means that you can decode stimulus, image orientation, image angle. But this doesn't necessarily mean that the brain is encoding physical things. This brain may be representing a mental state or perceptual state. The top part shows the decoder trained with stimulus physical image in this brain activity. At the bottom part, this person, the subject is just imaging the right tilted grating. From that brain activity, we can accurately decode whether the orientation is left tilted or right tilted. The brain signals encode both physical and perceptual experience. We are interested in vision, and the visual information comes from the eyes. And interestingly, that visual information goes to the back, the brain first, the entrance part called V1. V1 means primary first visual cortex, and then it relates forward V2, V4, and IT, and goes to some hierarchical processing. And at V1, we can see orientation and edge selective neurons. But as you go up higher, neurons in those higher areas tend to be activated by more complex shapes. And this ID part, you can find many neurons which are selectively activated by human faces, for instance. So this is human brain biology. Now we have a good model of human visual cortical hierarchy, which is a deep neural network that often used AI for computer vision. It called CNN, convolutional neural network. The architecture is inspired by the study of Hubert Roussel and the others. I don't explain the technical details now, but you can check Horikawa and Kamitani's paper. Horikawa and Kamitani found that we can predict how deep neural network responds by just looking at the brain activity pattern. So we can translate one brain activity to AI signal again by using machine learning. So this is the basis for image reconstruction used in the visuals of dissonant imaginary installation at Pompidou Center. So again, we have fMRI signals induced by some images or just by imaging. This is translated into deep neural network signals. Here I'm calling decoded features. What we wanted to do is to make an image that is a reconstruction of what we are seeing. So we want to read the mind perception from the brain as an image. But what's predicted from the brain is those features, and we want to know what kind of image input gives a rise to those predicted deep neural network features. That's a reverse inverse program, and it is difficult to get the signal mathematical formula. So right now we are doing optimization of images, which means that we start from some random images, then calculate the DNN features, and finally compare with brain recorded deep neural network features. We try to minimize the difference by changing the value of individual pixel input. That's how we get the reconstruction. Additionally, we use the generator network on the left, which is so-called GAN. We just use it to make the image a little bit smoother. The left is perceived image and the right is generated image by using GAN. So you see, so this does not read the exact copy, but you can see the something similar. So we are interested in dissonant imagery was the interaction between vision and audition. Visual area of the brain is at the back of the head, this green part of the right side. The auditory cortex is in the middle, the purple part. They are a little separated, but they are in the same brain and actually communicating by their neurons and spikes. So this is the same pictures as before, but we changed was this. So instead of showing images, we presented sound while keeping the all the models and all the decoders are the same. Here we look at the visual cortex and we are interested in visual cortical activity induced by sound. And we get some reconstruction. So this can be some automatic response, but also you spontaneously imagine concrete things from sound on. This is some example visuals, so it's shown in the visual at Pompidou Center, the exhibition. So depending on what you hear, reconstruction from the brain visual parts is different. What's significant about this work is that it translates sound into visuals in a unique way without relying on ideas or narratives that has been used traditionally. There are so many more to be developed, but I also believe that improvement in the quality and accuracy will open up more possibility. I also can see that this will be applied to dance performance or architectural project, as well as audiovisual works like dissonant imagery. Last but not least, I like to show my appreciation to Dr. Kamitani for this great chance. Thank you.